Hello everyone, let's analyze. So today we're going to talk about the inverse function theorem. So let's give the hypothesis. Suppose f maps an open subset of Rn to Rn is class Cp. That means I can take p derivatives of f and all of those derivatives would be continuous. P is at least 1. And also the derivative at x naught is invertible. Right? So that's what we're assuming. If all of those things are true, oh, by the way, the fact that the matrix at x naught is invertible, that's equivalent to saying that the determinant of that matrix is not 0. Okay, so if all these things are true, then there exists an open subset of A containing x naught for which f is invertible on U. And the inverse function maps f of u to u is class Cp. Furthermore, the derivative of the inverse at y in f of u is given by the derivative of f at x inverted. So we're going to prove this. The proof is what you may call way hardcore. It's intense. However, each step of the way we will be using material and results that we've proven in the past. So you may have to pause and digest throughout the proof, but each piece of the proof should make sense. So before I get into the nitty-gritty, let me give you an outline of what we're going to do. So we're going to prove the case for a simplified theorem first. We're going to prove the theorem when we add the conditions x naught is 0, f of x naught is 0, and the derivative of f at x naught is the identity. So assuming that, we're going to prove that for any y in some neighborhood of 0, there's a unique x such that f of x equals y. This is the invertibility condition. By using a potent combination of the continuity of f, the mean value theorem, and contraction mapping to argue that this function gy of x, defined as x minus f of x minus y, has a unique fixed point in some open ball centered at 0. We'll use the debris of this previous machinery developed to show the result A to continue showing that f inverse is continuous. And we'll show that f inverse is differentiable by asserting the Cp class of f and that the set of all non-singular matrices of size n by n is open in the set of all matrices of size n by n. Non-singular just means invertible, by the way. We'll show that f inverse is class Cp by an induction step and invoking the class of f and the continuity class of the inverse function. The inverse function is just defined as the inverse of the argument matrix A. The inverse of A is, well, the inverse of A. It's C infinity, in fact, because I can actually construct the inverse of a matrix where each entry of the inverse is just a polynomial of the entries of A. And that's where we get the C infinity class of the inverse function. And then we'll prove the general case. If the derivative is not the identity, then we'll create this function g of x, which is equal to the inverse of the derivative of f at x naught times f of x. Well, then the derivative of g at x naught is the identity, and g is invertible. And from the inverse of g, we can construct the inverse of f. Now, if x naught is not 0 and f of x naught is not 0, then we can construct h of x to be f of x naught plus x minus f of x naught, and then h of 0 is 0, which means h is invertible, and we can use the inverse of h to construct the inverse of f using the formula given. So that's a roadmap of how we're going to prove it. We'll go outline item by outline item. Hold on to your seat. Feel free to press pause when needed and digest the pieces. Okay, so first let's consider the simplified case. X naught equals 0, f of x naught equals 0, and the derivative of f at x naught is the identity. So our goal for part A is to show that for each y in some open set containing f of x naught, that is 0, there's a unique x such that f of x equals y. So let's define this g function to be x minus f of x. Note that the derivative of g at 0 is the derivative of x, which is the identity, minus the derivative of f at 0, which is the identity, and the identity minus the identity is 0. Also, g of 0 equals 0 minus 0, which is very 0. Note also that because x is C infinity and f is class CP, then both combine to show that g is class CP, meaning that the derivative is continuous. Then there exists some delta 1 greater than 0 such that if x minus x naught is less than delta 1, then the derivative of the ith entry of g, now remember f has a domain in Rn, so f can be thought of as f1, f2 through fn, and similarly for g. Minus the derivative of the ith entry of g at x naught is less than, well, whatever I like, so long as it's positive. I like 1 over 2n. So I can find a delta 1 that can guarantee this result. That is, since x naught is 0, if x is in the open ball centered at 0 of radius delta 1, then the derivative of gi of x, which by the way is just equal to the gradient of g of the ith entry, because the derivative is the transpose of this, but the transpose doesn't affect the norm, is less than 1 over 2n. That's because this term is 0 from this condition. Well, the mean value theorem implies that there exists n vectors, c1 through cn, contained in the interval connecting 0 to x, which is contained in the open ball centered at 0 radius delta 1, such that gi of x minus gi of x naught is equal to the derivative of g at ci times x minus x naught. Well, since this term is 0, this is just gi of x, and this is the gradient of gi at ci transpose x, because x naught is 0 in our simplified case. It follows that the norm of g of x, remember g of x is a vector in Rn, and when we say norm, we mean the 2 norm, and I'm actually going to write it here because I'm going to use this relationship between the 2 norm and the 1 norm, which is defined to be the sum of the absolute entries of gi from I equals 1 through n. By the way, could you prove this? I think you could prove it. Expanding g into the canonical basis and then using the triangle inequality would give you this result. It would be a good challenge for you. And then using this equality, this equals the sum of the absolute value of the gradient of gi at ci transpose x, which is less than or equal to, and here's our opportunity to use the Schwartz, the Cauchy-Schwartz, the norm of the gradient of gi at ci times the norm of x. Now because ci is contained in this ball, I get this result is true. So this is less than 1 over 2n, and this is less than delta 1. So the norm of g of x is less than the norm of x divided by 2. If I add 1 over 2n n times, I get half. And of course, that's less than delta 1 over 2. So it follows that g maps the open ball of radius delta 1 into the open ball of half delta 1. And in fact, g maps the closure into the closure, right? And I can close the sets if I choose delta 1 so that this is completely contained in A. So I can close the sets by the continuity of G. So now let's define gy of x to be y plus g of x, which is y plus x minus f of x. Now, our goal is to show that this is in fact a contraction with a unique fixed point. And if I have a unique fixed point x, I have a unique x such that x equals f of x. I'm sorry, such that y equals f of x. So let x be in the closed ball of radius delta 1, then the norm of gy of x is equal to the norm of y plus g of x, which is less than or equal to y plus g of x. Now we know that this is less than or equal to delta 1 over 2 from this condition here. So then let us suppose that this is less than or equal to delta 1 over 2. So then this is less than or equal to delta 1 if y is contained in the closed ball of radius delta 1 over 2. So this shows that gy applied to the closed ball 0 to delta 1 is contained in the closed ball 0 to delta 1. So now let's show the contraction property. Let x1 and x2 be in this closed ball. By the way, a closed ball in Rn is a complete metric space. Then the norm of the difference of gy applied to x1 and gy applied to x2, of course we have to show is less than a number strictly less than 1 times the norm of x1 minus x2. Well, this is equal to y plus g of x1 minus y minus g of x2. Of course, y minus y cancels. And that's less than or equal to the sum from I equals 1 through n of the norm of gi of ci times x1 minus x2 using the same mean value theorem machinery as before. And of course, because Ci is contained in the open ball, each of these terms are less than 1 over 2n. It follows that gy of x1 minus gy of x2 is less than or equal to 1/2 times x1 minus x2, implying that gy is a contraction. So if gy is a contraction, we get our result because for each y in the closed ball of radius delta 1 over 2, there exists a unique fixed point of gy. In other words, a unique x that's equal to gy of x, which equals y plus x minus f of x. Implying y equals f of x. Therefore, an inverse exists. F inverse, which maps the closed ball of radius delta 1 over 2 to the closed ball of radius delta 1. So let's use what we've derived to show that f inverse is continuous. Now, we're going to show that f inverse is differentiable, which you might think makes this redundant, but we're actually going to use this continuity result to show f inverse is differentiable. Well, to show a continuity proof, we start with our familiar place. Let epsilon be positive. Suppose that y1 minus y2 is less than epsilon over 2. And of course, y1 and y2 are both in the domain of the inverse, which is the closed ball of radius delta 1 over 2. Well, that means x1 is the inverse of f1, which is contained in the closed ball of radius delta 1, and x2 is f inverse of y2, which is also in the closed ball of delta 2, because the inverse maps the ball of half the delta 1 radius to the closed ball of delta 2 radius. So the difference of these two, f inverse of y1 minus f inverse of y2, right, of course we got to show this is less than delta. Well, this equals x1 minus x2, and remember that x1 and x2 are fixed points of g y1 and g y2 respectively. Which equals y1 plus g of x1 minus y2 minus g of x2 by the definition of gy, which is less than or equal to y1 minus y2 plus g of x1 minus g of x2 by way of a simple triangle inequality. And that's less than y1 minus y2. And recall that we know that this difference is less than 1/2 x1 minus x2. This comes from the contraction property of gy of x, which equals y1 minus 2 plus 1/2 f inverse of y1 minus f inverse of y2. Now if I subtract this term from where we started, I get 1/2 f inverse of y1 minus f inverse of y2 is less than or equal to y1 minus y2. By just subtracting this from where we started, I'll multiply both sides by 2. And of course y1 minus y2 is less than epsilon over 2. So this is less than 2 times epsilon over 2, which is epsilon. And so we've proven continuity. We've actually proven something even a little stronger. We've actually proved a Lipschitz condition. This inequality here implies a Lipschitz condition. I think it's just 1p. I'm not sure. Let's go with 1p for now, which is an even stronger form of continuity. So our next task, part C, is to prove that f inverse is differentiable, and the derivative at y equals f of x is the derivative of f at x inverted. Well, we know that the derivative of f at x naught for a simplified problem is the identity, which is invertible. So it's in the set of all invertible or non-singular n by n matrices, which is an open subset of R n by n. The derivative is a continuous mapping from A in Rn to n by n. Since f is Cp, meaning that df is class Cp minus 1. So there exists some other delta, we'll call it delta 2, such that df of x is invertible. Remember, this is a matrix, so we're saying that this matrix is invertible for all x in this open ball of radius delta 2 centered at 0. Of course, we can think of this open ball as being contained in the preimage of the set of all non-singular matrices with respect to the function df, right? So because this is open, the preimage of this continuous function is open, so therefore x is contained in this open ball within this preimage. So we now have two deltas running around, delta 1 and delta 2. Let delta equal the min of them. Now let y1 and y2 both be contained in the open ball centered at 0 of radius half a delta, and x1 is the inverse of y1, x2 is the inverse of y2. We'd like to show that the derivative is differentiable and that the derivative is given by the inverse of this matrix. So f inverse of y1 minus f inverse of y2. Now as y1 goes to y2, right, I want to show that the definition of the derivative satisfies the correct limit. So let me put what I conjecture my derivative is. Right? It's the derivative of f at x2 and then that matrix inverted. Times y1 minus 2. Divided by y1 minus y2. So if I can show this goes to 0 as y1 goes to y2, then I win the day. So this equals the norm of x1 minus x2 minus this inverse of the derivative. Of course, y1 is f of x1 minus f of x2, again divided by y1 minus y2. So I can factor out this matrix here. Since I'm factoring out of the whole term, I have to multiply this by the inverse of this inverse, which is just the derivative matrix at x2 plus f of x2 minus f of x1 divided by y1 minus y2. Now we can kind of see where we're going. We know that this, if I divide by the norm of x2 minus x1, is going to converge to 0 because f is invertible. But I need x1 minus x2 in the denominator. So, well, let me multiply and divide by that then. So this is less than or equal to the norm of this matrix. Right? Again, the norm of a matrix is defined in terms of the operator norm. And the definition of the operator norm is what allows us to give this inequality. I'm going to rearrange this a bit. You may notice that in my rearranging, I also multiplied by -1, but I'm allowed to do that instead of a norm. Divided by x1 minus x2 times x1, which is f inverse of y1, minus x2, which is f inverse of y2, now notice I switched these places, so divided by y1 minus y2. Now, remember we showed that f inverse is continuous. We showed it was not only continuous, it was specifically Lipschitz continuous. So this numerator is less than 2 times the denominator. So the denominator cancels and I get that this entire thing is less than 2. By the Lipschitz continuity of f inverse. So then this is less than or equal to 2 times the derivative at x2 inverted, of course the matrix at this particular point inverted, times f of x1 minus f of x2 minus the derivative now this term goes to 0 as x1 goes to x2 because f is differentiable at x2. Of course, this is just a matrix that's invertible. It has some norm, and 2, like this, is also just some number. that doesn't change as x1 approaches x2, and neither does this as x1 approaches x2. So this entire term goes to 0. As y1 approaches y2. Of course, as x1 approaches x2, y1 approaches y2 by continuity of f. So we've concluded that f is invertible on the preimage of the open ball of radius delta over 2 centered at 0, and the derivative at y is the derivative at the inverse image of y. So now we use an induction proof to show that the inverse function is Cp. What do we know? We know that F inverse, which maps an open ball contained in A, contained in Rn to Rn, is continuous. So we know that. We know that the derivative of F, right, maps A in Rn to Rn by n is continuous. Right, we know that by hypothesis because F is class Cp. So in fact, dF is class C, p minus 1. And the inverse function, which maps non-singular or invertible matrices to non-singular matrices, is continuous. In fact, it's class C infinity. That's true because we can actually construct the inverse of a matrix where each entry is essentially equal to a polynomial of the entries of the matrix being inverted. Which is why we can get class C infinity. What follows then, that the inverse of the derivative function of f inverse maps the open ball of radius delta over 2 to a n by n non-singular matrix is continuous. And while the derivative of f inverse at y is equal to, from our previous result, the inverse of the derivative at f inverse of y, right? Take the inverse of that matrix, which is exactly this composition of y. Therefore, this is continuous because this is exactly this. So, not only is f inverse continuous and differentiable, but the derivative is continuous, right? The derivative of f inverse is continuous. Therefore, f inverse is, we know now, class C1. Now let's repeat. The inverse of f the derivative of f inverse at y equals the inverse of, or composed with, the derivative of f composed with f inverse of y. This is C infinity. This is class Cp minus 1. And this is class C1. Then the f inverse is also class C1, which implies f inverse is C2. Not only is f inverse continuous and differentiable, but the derivative is continuous and differentiable, and that derivative is continuous. Now, how does the convolution of C infinity, Cp minus 1, and C1 class functions imply that the entire convolution is C1? Well, we can show that by taking or applying the chain rule and a combination of the product rule to show that the continuity class of this convolution is equal to the minimum class. But now we've raised the minimum class from C1 to C2. So let's write it again. Right, we have the same composition formula for df inverse. This again is C infinity. This is Cp minus 1. And now this is C2. Then df inverse is C2, implying f inverse is C3. Well, if we continue this line of argument, df inverse of y, again, it's equal to the same composition. Eventually we'll get that this is class Cp minus 1. This is still class Cp minus 1, and this is still class C infinity. Then df inverse is Cp minus 1 class, implying that f inverse is class Cp. And we've shown our result for D in the outline, that f inverse is Cp. So now that we've proved the theorem for the specific case, let's consider the general case that x naught is not 0, or f of x naught is not 0, or and the derivative at x naught is not the identity. Well, let's consider this generalization, that the derivative is not the identity, it's some matrix T. But of course, according to the assumption of the hypothesis of the theorem, the matrix is still invertible. Well, let g of x be T inverse times f of x. then the derivative of g at x naught is t inverse, well that's just a linear operator, times the derivative of f at x naught, which is t inverse times t, which is the identity. And of course, if f of x naught is 0, then so is g of x naught. So g is invertible. So the universe exists for some neighborhood of 0 or of x naught. And so is f inverse. It's g inverse composed with the linear mapping, the inverse of t. Because if x is g inverse of t inverse times y, then g of x is t inverse times y. Of course, g of x is t inverse times f of x, which is t inverse times y. If I multiply both sides by t, I get f of x is equal to y. So suppose x naught is not 0 and or f of x naught is not 0. Well, no problem. Let h of x be f of x naught plus x minus f of x naught. Notice that h of 0 is f of x naught minus f of x naught, which is 0. So h, no matter what its derivative is, so long as it's invertible, and of course it has to be because the derivative of f at x naught is invertible. Therefore, h inverse exists in some open neighborhood of 0. Then f inverse of y exists as well, and it's given by the expression h inverse of y minus f of x naught plus x naught, since if x equals h inverse of y minus f of x naught plus x naught, and subtract x naught from both sides, h of x minus x naught is therefore equal to y minus f of x naught. And this, by definition, is f of x naught plus x minus x naught minus f of x naught. Add f of x naught to both sides. X naught minus x naught cancels. And I get f of x is equal to y. And that concludes the inverse function theorem. Massive, I know. So let's consider an example. Let's suppose that U maps R2 to R2. Let's show that this is locally invertible near every point, even if it's not globally invertible. By the way, I should point out that showing that U is locally invertible is the same as showing e to the z for a complex number z is locally invertible, which means the natural logarithm can be extended to the complex plane, at least for a portion. So note that the derivative of u, is a matrix with two rows. Each row is the transpose of the corresponding entry of u. So the first row is the transpose of the gradient of u1. The second row is the transpose of the gradient of u2. And I get that matrix on the right. The determinant of this matrix is equal to e to the 2x1. And that's never 0, no matter what x1 is. Also, the derivative is continuous. So I've satisfied the conditions of the inverse function theorem. So I'm guaranteed that everywhere my function is locally invertible. Furthermore, if y is equal to u of x, the derivative of the inverse of y is given by the derivative of u at x inverted. Of course, we have a simple formula for the inverse of a 2 by 2. It's 1 over the determinant times we switch the diagonal entries and flip the sign on the off diagonal, and we get a matrix. So we can actually say exactly what the derivative is at each y in the codomain of u. Of course, the reason that it's not globally invertible is that if I evaluate u at x and u at x plus 2 pi e2, which means I add 2 pi to the x2 term, well, then I get the same thing. So I can't be invertible globally. Well, that's all for today.